Yeah, sorry for this 5 minutes delay. And well, I mean, first of all, thank you very much for inviting me. So this is quite an inspiring workshop. I'm learning a lot. And so I'll be talking about a different aspect of spin flow, an approach from gauge gravity duality. So I'll be talking about holography or gauge gravity duality. And this is a very, well, a paper from April, a recent paper based, so this talk is going to be based on that paper with my student Domingo Gallegos. And so I just want to mention also that this is, this talk will have a little bit of a different spirit than the previous talks, in the sense that I'm not going to be, I will be motivated by the data, of course, by the experiment, but not the phenomenology. So that will be more like a theory talk, establishing the aspects of spin flow. So first of all, I just want to make the point that, of course, we are all interested in understanding how the spin flows in quark-gluon plasma, but this subject of spin transport is quite broad, and it goes all the way to spintronics and this recent field of liquid spintronics, the liquid spin flow in liquid metals, and graphene and Dirac and Weil semimetals, etc. So this is it will be quite important to understand how precisely spin and flow is related to the other collective flow in all of these systems. And of course, for us high energy physicists, the main motivation is the quark-gluon plasma. And I don't, for this audience, I don't think that I need to explain this slide in detail. Everybody knows this amazing result, this spin induced by vorticity in the quark-gluon plasma. And the only point I want to make here is, if you can see the arrow, that the vorticity is essentially produced by the differences of these, the difference of these velocity fields, and that produces some vorticity, as this is the expectation, and the vorticity as a result of the spin-orbit coupling produces some global hyperon polarization. But there may be other effects in play, so it will be quite important to understand all kind of transport that are related to spin to establish this number precisely, to put some error bars on this number, I think. And well, this is another experiment that was carried out recently, relatively recently, 1 year before the quark-gluon plasma observation. So this is in liquid spintronics. What you see here is essentially, so you can, as you all know, by just the Lorentz force, you can produce some electric voltage across a tube if some fluid is flowing in the tube in the presence of a magnetic field. But essentially, the idea here is the same, that you have a fluid flowing in a tube, but instead of a magnetic field, you have some kind of some vorticity, again perpendicular to the flow, and that produces some spin voltage. So this is the basic idea, and this idea was realized in experiments by Takahashi et al. And this is a Nature paper in 2016, and where you see that this velocity gradient is provided by the fact that there's a friction at the walls of the tube, and in the middle the velocity gradient is much higher. So this produces some vorticity, which aligns the spins of the particles inside the flow. So this is some liquid metal that produces some spin flow along with along the gradient of the vorticity, and some spin chemical potential proportional to the vorticity. So this is more or less the same effect that we see. So this is the only point I'm trying to make here, is that both in high energy and low energy physics, the spin transport is playing quite an important role, and there are many experiments going on. So we need to really establish the basic features of spin flow. And as a disclaimer, I just want to comment that I'm a newcomer to this field, so I may not be, my referencing may be incomplete, so I just apologize from the beginning. Of course, I know that many people are working on, have been working on spin transport for a long time. I just started. With that, let me continue. So what we need to do to understand the spin transport in all of these systems, in these strongly correlated systems, we need to establish one thing that one can try to do is to establish the hydrodynamics with the spin current. So that means essentially to, first of all, classify all possible sources of spin density and current, and establish the relationship between spin flow and the other kind of collective phenomena like energy, charge, momentum, chirality flow, and also classify and compute, if possible, the spin transport coefficients. So in essence, what we need is a construction of hydrodynamics with spin. Okay, so there's energy momentum tensor and the spin current. So before going to holography, what I will do is I will try to establish this, the basics of this hydrodynamics that is already known to many of you. And then I will go and see what holography can, I will tell you what holography can tell us about these spin transport coefficients. So this is where the holography comes in to compute these spin transport coefficients essentially. Okay, so the most, I think, exhaustive and generic approach to hydrodynamics would be using an action formalism. So starting with an effective action. This is also what we do in quantum field theory. Starting with so considering some quantum field in a non-trivial representation with some non-trivial spin, and defining the effective action by this path integral in the presence of sources. So what are these sources? If you want to have, if you want to source energy momentum tensor, you need a field bind. If you want to source spin, you need a spin connection. So these E and omega are the spin connection, are the field bind and the spin connection respectively. And then you can make a variation of the effective action with respect to the field bind to obtain the energy momentum tensor. And if you do this with respect to the spin connection, you get the spin current. Okay. So this is this is the Einstein-Cartan formalism, and in general, the reason most of the time the reason that we are not using this formalism, you can, but the reason that we don't need this formalism is because the spin connection is given complete in terms of the energy momentum, in terms of the field bind, in the absence of torsion. So torsion, let me remind you, is like the covariant derivative of the field bind, with the gauge field, the role of the gauge field being played by the spin connection. And when this quantity is zero, when there's no space-time torsion, as like in quark-gluon plasma, for example, when in the absence of any torsion, this spin connection is completely determined in terms of the field bind. And if you take into account this connection, when this is zero, when you make the variation with respect to the field bind, what you get is precisely the Belinfante-Rosenfeld energy momentum tensor. Okay. So it has essentially this connection, this combination is precisely that pseudo gauge transformation that you have in the definition of the energy momentum tensor. Okay. So there is some ambiguity in the absence of torsion, but this ambiguity is at least partially removed by the presence of torsion. Okay, so torsion removes this ambiguity. So, so what I propose to do now is, so when you want to establish a hydrodynamic theory of any kind of collective phenomena, you have to establish the zeroth order sources in derivatives first. So the zeroth order source here, if you like, you can think of it as a zeroth or higher order in derivatives, but the torsion would be a zeroth order source in principle. And which is, so if you want to keep your zeroth order sources in this derivation of this formalism, then you need to turn on torsion. And in the end, of course, in quark-gluon plasma, we know that there is no space-time torsion. So at the end of the calculation, you can set the torsion to zero. But you can use, just like using magnetic fields in the Ising model to determine the magnetism, and then you can set it to zero. This here you can first turn on, keep some non-zero torsion, and then at the end of the calculation you can set it to zero, but you can calculate the response, which will be the spin current. So here it is. It will be a little bit easier to formulate hydrodynamics using contortion rather than torsion. So contortion, let me remind you, is the non-trivial part of the spin connection due to the presence of torsion. So in the absence of torsion, the spin connection will be completely given by the Levi-Civita spin connection that is just given by the derivatives of the field bind. So in the end, what I want to do, I want to formulate this problem in the presence of non-trivial E and omega, and at the end I will just set the field bind to 1, that is just flat space. So this will be gone, but here this will be non-trivial. So I will just take a variation with respect to the contortion to obtain the spin current, and then set the contortion to 0 if you want. Okay. So that is the procedure. And in passing, I just want to make a comment that this torsion, the presence of torsion, even though we know that in quark-gluon plasma it is not there, in most of these interesting problems that I listed here, so in graphene, for example, in Dirac-Weil semimetals, in liquid spintronics and all of that, the torsion plays some kind of role, some important role. So it's essentially for example, in graphene, you can always introduce some dislocations in the atomic structure of the torsion, or in the atomic structure of the graphene, and that is exactly what I mean by torsion. So in condensed matter, torsion is playing some interesting role, and in a continuum limit where you take a low energy limit and describe this the dynamics by using hydrodynamics, this torsion will be essentially just describing, it will be sourcing the spin flow. So here it is just a picture of what torsion is. So if you take, if you have, for example, two vectors that are perpendicular to each other, if you just parallel transport one vector with respect to the other one by the other one, if they don't match up at the same space-time point, if there is some kind of a Burgers vector that are going from here and going from there is different, then this is essentially torsion. So this is essentially the difference between these transported vectors m prime and n prime can be is proportional to this this torsion two form. Okay. So this is just a comment in passing. So how do we define the hydrodynamic equations? First of all, how do we derive them from this action? Well, what you need is to establish the symmetries in the problem. So the local symmetries. So as usual in hydrodynamics with some, for example, charged fluid, what you do is you derive the energy momentum conservation and the charge conservation by using the diffeomorphism symmetry and the gauge symmetry, the U1 gauge symmetry. So here what we need to do, in analogy to that, what we need to do is to apply diffeomorphism transformations on the field bind and the spin connection. These are just given by these Lie derivatives along some psi vector, and the local Lorentz transformation. So both the field bind and the spin connection are charged under the local Lorentz transformation. So if you start with this effective action and make these Lorentz transformations, then what you get, if you demand that the effective action is invariant under these symmetries, what you get is first one, diffeomorphisms gives you this equation. This is an equation that most of the people here in the audience knows very well. The only thing that I'm commenting here is that in the presence of contortion, which is the most general case, there is a new term that maybe some of you don't know. So this is this zero, this ring essentially is the covariant derivative with respect to the Levi-Civita connection. So this would be essentially just a normal partial derivative in flat space. So you can think of it just the partial d mu. And on the right hand side, what you have is a work term. This is like the analogous to the current here, and this is just like the analogous to the energy, so to the electric field. So this is like a work term, and there is another work term in the presence of torsion. Okay, so this is the antisymmetric part of the energy momentum tensor, and this is the contortion. And the spin current, so from the local Lorentz transformations, you get the equation for the spin current. On the right-hand side, as we have discussed already in this workshop, there's the antisymmetric part of the energy momentum tensor. But in the presence of contortion, there's also this term that couples to the spin current. So this means essentially that even when the energy momentum tensor is symmetric, you may get a non-trivial spin current by solving these equations in the presence of contortion. Okay, by the way, if you have any questions, please stop me, because I don't know if most of the people can follow this. There is a lot of formalism here, so just please stop me and ask questions if something is not clear. So the thing that you need to do then, okay, the most general thing, as usual in the construction of any hydrodynamic approach in a Lorentz invariant theory, is that you need to decompose the sources in a Lorentz. You have to subject your sources to a Lorentz invariant decomposition. And in this case, our sources, the field bind, the composition of the field bind is well known, but the composition of the spin connection is something somewhat new. So the spin connection has essentially in 4 dimensions, it has this antisymmetric indices AB that is like 6 degrees of freedom. And there's of course, this is a vector. So there's a mu index that is hidden here that gives you 24 degrees of freedom. And these 24 degrees of freedom should be decomposed by using Lorentz symmetry and by the fact that there is a time-like killing vector that essentially defines the flow of the fluid, u mu. So this can be done by introducing this vector. There's a vector part like this, and there's an axial part. You can introduce this, and the rest will be just some tensor. So there will be, so this is 4, there is another 4, and the rest is 16 in the tensor. And these 4 degrees of freedom can further be decomposed by proportional to u mu. So it's something like a chemical potential and the transverse direction. So that will give you one scalar, so mu a, that comes from this one, another scalar, mu v, that comes from this one, u dot this, and the rest, the transverse parts, will be just a1 and v1. And then there's going to be like these tensor parts. So as you can see here, there will be two traceless transverse symmetric tensors. So this H and C, and 2 axial transverse vectors, A1 and A2. And there's V1 and V2, two vectors, and one scalar, mu A, one pseudoscalar. So I want to make a connection with, I want to make a comment here with, and connect this decomposition to the previous talk. So for example, this mu A and this A1 is, sorry, A2 is going to be precisely this, this axial charge, okay? So mu A is going to be the axial charge. So this decomposition, this already includes the axial effects as well. So if you just consider this spin connection as a source, that also sources the axial transport. Okay, so I will come back to this when we discuss some examples. Okay, so then what the next thing that you need to do in the hydrodynamic approximation, in the approach to establish the constitutive relations. So since we are talking about a situation where the energy momentum tensor can have an antisymmetric part, we need to be more general and include these, for example, there can be 2 different heat currents in different, so this Q and Q bar can be different when you exchange mu and nu indices. They don't have to be the same because of the antisymmetry. And there can be some antisymmetric part that is different than this. So this will be something like perpendicular to all of that. So this will be something like an intrinsic torque, as well as, of course, the symmetric part should be included, which will, for example, include the shear and the bulk viscosities and all of that in the higher derivative, in the higher orders in the derivative expansion. And similarly, by using these sources, so decomposition of these sources, you can also decompose, in the most general sense, the spin current, and this will be the decomposition. I don't expect, I'm not going to go through all of these terms here. The only thing I want to make a comment is that this first term is exactly of the same form of this Frankel-Weisenhoff spin flow, and the rest is just giving this contribution to the perpendicular part. Okay. So, as a summary, we have the spin source, that comes from the spin connection or contortion, that are the same thing. Those are the same thing in the absence of curvature in space. So in flat space, they are the same thing. And furthermore, this contortion can be decomposed into these sources that are. So this will be, for example, like an axial charge, axial chemical potential, but the rest will be spin flow. Okay, and this will be like a normal chemical potential for the vector part. So the spin current has this corresponding decomposition. All right. So now let me finally come to the main point of this talk. After all of establishing all of that, but since I started a bit late, I want to know exactly how much time I have for holography.
I think you should have another 15 to 20 minutes.
15 is fine, perfectly
okay,
fine.
Good.
Okay. So this is a point to. If you have any questions, please ask me now about this decomposition. So here, just let me stop for like 10 seconds.
May I ask, you introduced the spin current, you have a quite rich hydrodynamics. Would it mean that you have something besides the Navier-Stokes equations? Because we have finally Navier-Stokes coming from energy momentum conservation, from energy momentum tensor.
Yeah. So, well, so essentially you have, so this is a coupled system.
Mm-hmm.
So you have this is the Navier-Stokes equation. So if you just forget about, for example, curvature, we don't need curvature. So set this term to 0. Let's simplify our life. And this is some contortion, which in the end of the day, I will also set to 0. So this will be the Navier-Stokes equation. And then there's going to be this term, this spin current with that couples to the antisymmetric part of the energy momentum tensor.
So this means some more rich just equations.
That will be richer equations. Right, but so in view of connecting to the experiment, I'm not going to comment on that because I don't really know how much this back reaction of the spin current on the energy momentum tensor is relevant for data. I don't know. Probably not much. So this will be this kind of, I think, more general coupled system of equations of motion will be more relevant for situations like in condensed matter, like the one that I just showed in graphene, when you have dislocations. And this have a lot of applications because that means essentially you can use torsion to source spin current. So this is one of the biggest problems in spintronics to establish some coherent spin flow. And torsion can be used for that. So that's essentially the idea. But in general, yes, if you are interested in just establishing the theory by including all the sources and the response, then indeed, so these two equations should be considered general. Okay. Any other questions? Right. So let me.
Umut, could I interrupt?
Sure.
Yes, I just wonder, so here in writing down the decomposition of stress tensor, do you assume any frame?
Right, perfect question. No, but of course there will be some frame dependence. So, so essentially, well, here, I mean, there will be some frame dependence, especially if you also turn on charge, right? So U1. So there will be Eckart frame and there will be Landau frame. So, but here this, but I want to, I mean, I have to, okay, so thanks for asking this because this is, I don't want to give the impression that we understand everything in this decomposition. So this is a work that is quite recent and we have a lot of questions in mind. And one of those questions is how much of this decomposition is affected by for example, by the pseudo gauge transformations. Another question is what are the quantities that you can derive that are frame independent? So for example, these heat currents, are they, how much frame dependence is there in the heat currents? Mm-hmm. So this is a very good question. Yes, I don't have a very clear answer to it.
Just a quick question. Is there an entropy definition?
Yes, perfect question. I will come back to that in the end. There is an entropy definition, of course, but it is not very. Yeah, let's discuss that in the discussion maybe. That's a very long discussion. So a quick comment is that we are now working on that, and we want to derive the entropy current again, starting from the effective action. But it is not an easy thing to do because you have to include all the dissipative terms as well. So the first order in derivative terms should be included. If you don't include them, you get some inconsistent results. So it turns out to be a harder computation than the usual case, but this is ongoing work. Okay, so let's open this discussion again if you like at the end of the talk. Thanks for asking. Okay, so let me now. So this is just to establish the setting, what we want to do. So this is the field theory background, and what we want to do by using holography is to, in principle, to be able to calculate spin transport coefficients, just like the usual ordinary transport coefficients, for example, shear, viscosity, bulk viscosity, at least in some toy models like conformal fluids. But that would be a good start. So maybe I should remind some of the people in the audience that the holography is, well, gauge gravity duality is summarized in this picture. So essentially, there is some a strongly coupled large and gauge theory is dual. There is a duality between strongly coupled large and gauge theory and semi-classical gravity in asymptotically ADS spacetimes. So this is a sketch of an asymptotically ADS spacetime with a boundary, and there is a black hole in the center. There is a horizon of the black hole, and the collective transport on the boundary. So I'm assuming that there's some plasma on the boundary, and this collective transport in this plasma that is here shown by this arrow J, some current, is mapped by some bulk fields to the fluctuations around the horizon. So essentially, if you want to source this current J on the boundary, you need to introduce some electric field, say, and that electric field in the dual picture will send some bulk gauge fields towards the horizon, and from the infalling boundary conditions of this gauge field, you will be able to read off the response to that source. So essentially, this bulk gauge field, how it falls in the horizon, tells you how the response is determined. So this is holography. So it has the potential to tell you this to transport coefficients in general. And this is of course the Hall of Fame which established this result, starting from Toft, ending with Polyakov. So one important thing about this holography is that you may get lucky, and there may be some generic properties of this collective flow on the boundary that can be read off from the universal properties of the horizon geometry. So the horizons turn out to have universal geometries, and for one famous example that we know is that regardless of what kind of holographic theory that you have here, assuming that it's an Einstein gravity coupled to some arbitrary matter field, what you have is the shear viscosity, for example, that you obtain by using this holographic approach is 1/4 pi. So this is the famous result of Policastro, Sonstad, and Compton in 2001 and 4. So one main motivation for me is, can we find similar universality in spin transport? Okay, so that would be quite nice. And I will try to answer this question. I'm not going to be able to provide a final answer to this question. Obviously, this is just starting the discussion. So we want to do the same thing for the spin flow. So instead of a current, an electric current here, we have a spin current. And the spin current, as I discussed, is sourced by some spin connection or torsion or contortion or something like that on the boundary. And then this will source a bulk field. The bulk field will be this dynamical spin connection field that is falling towards the horizon. And again, from the infalling boundary conditions at the horizon, we should be able to read off the response and the relationship between the two. That coefficient will be the spin transport coefficient. Okay, so this is the radial direction. And that is, for that, what we need to do is, first of all, we need a formulation of gravity there where the first order formulation of gravity with independent field bind and independent spin connection. So normally in Einstein's formulation of gravity, these two are connected to each other. Okay, so these two, in the second order formulation, these two are related to each other. Spin connection is completely determined in terms of the field bind. But what we need is a different formulation. And that is one of the reasons that spin flow has not been really studied in detail in holography yet in the last 20 years or so. Because what we need is a different formulation than the usual case. We need a first order formulation. And it would also be quite practical if, especially in the calculation of these spin transport coefficients, if we can have analytic black hole solutions. So from there, we can read off numbers and the dependencies on temperature and things like that more precisely. And we can compare the coefficients with for example, the quantum field theory calculations. So for that, I will be using a somewhat unorthodox theory. This is the simplest theory that I can find, where in 5 dimensions, it has ADS-like solutions. So it is ADS gravity. It has asymptotically ADS solutions, like including black holes. And it's called the low-log Chern-Simons theory in 5 dimensions. I'm not going to explain it in detail. I will just flash this. Just mentioning essentially that this is like a Chern-Simons theory in 5 dimensions based on a group algebra that is SO4, 2. So that would be very important, for example, for establishing conformal dual to conformal plasmas. But in more so there is so you can relate it to the Einstein-Cartan theory in 5 dimensions by making the connection between this bulk gauge field by establishing it in terms of the field bind in 5 dimensions and the spin connection in 5 dimensions. So these are just the generators of translations and rotations in 5 dimensions. And the corresponding field strength, you can just plug this in, and then what you get is a first order gravity in 5 dimensions, which has only this, so which has the sources, these dynamical fields, field bind and the spin connection here. And it looks like this. So there is a cosmological constant term, there's a Ritchie scalar term, as we also have in Einstein theory. And then there's an additional Gauss-Bonnet-like term where the Gauss-Bonnet coupling is fixed to 1/4. So this is a very specific kind of theory, but this will be my toy theory. Okay, so to establish the basics. All right, so I'm not going to get into details of how to do calculations with this theory because this is completely, this is not the purpose of this talk. I will just show you the results. So, but the only thing I want to mention is that you can find analytic black hole solutions to this 5-dimensional theory, and this is one of the things that we did with my student. And by using those, you can see what kind of results that you get for the hydrodynamics and thermodynamics. So here I will be just first showing the first example. The first example is going to be there's a single axial source. So this is A2. So this is one of the sources that let me show you this table again. So there are all these different kind of sources that you can turn on. So here I'm just turning on this and setting all the rest to 0. And this is the result that you get. So there are some interesting observations. So first of all, this is a conformal fluid. So there is some temperature dependence, as you see here, T, and this kappa is a coefficient which stays in front of this action. So that is all over the place. So that should be fixed by data, if you like. This is conformal. How do I see that this is conformal? Because P is just minus 1/3 of the energy. So this is the pressure, this is the energy, and all the rest. So in this decomposition of the energy momentum tensor, all these terms are 0 except the energy, pressure, and this symmetric shear part of the tensor. So this is the result that you get. For example, there is no antisymmetric part. And this is the spin current. So this is the result for the spin current. So this is the source for the spin current. And there's a non-trivial spin current with a spin transport coefficient that is just, with a number, 32 pi squared times this kappa times T squared. And one comment that I want to make here is that this is, even though this is a symmetric energy momentum tensor, there is no antisymmetric part of this energy momentum tensor here. You get a non-trivial spin current essentially because you have this contortion. So you have the source. So this is just to remind you in this equation, this is 0 in this example, but you get a non-trivial spin current here because there is this K term, a component of this K term, this contortion term, which is A2. Okay, so this was one example. Let me go to another example, which is more complicated. Here you have both a vector charge, an axial charge, and a tensor charge. So it's still a conformal plasma. You can see that the energy is again minus 3 times the pressure. It's given by this. So all of these different sources, C, V2, and mu A, are entering in this result. And the reason that I want to show this is because this is an example where you have a non-trivial intrinsic torque. So there's an antisymmetric part of the energy momentum tensor. Apart from these heat currents that is also antisymmetric, there is also this non-trivial torque. Okay, and then you have an expression for the spin current. I mean, that's not really eliminating. The only thing that is nice is that there is the same spin transport coefficient appearing. So this is fine, but in the end, what we want to do is we really want to establish a connection that is closer to what is observed in the quark-gluon plasma and these liquid spintronics, which was based on, this is an observation of spin flow based on vorticity. So where is vorticity in this game? To see the vorticity, what you need to do is to go one order beyond in the hydrodynamic expansion, and you have to include the vorticity term in the first order in derivatives. To do this in holography, what we do is we follow the approach of fluid gravity correspondence. So that was established in 2008 by these people. What you do essentially is that you start with your black hole solution in your 5-dimensional action, and then you boost your black hole solution with some boost parameter, and then make these boost parameters depend on space-time. And then expanding this dependence on space-time in the boost parameters, you get an order by order connection to the hydrodynamics that is dual that lives on the background, on the boundary. Okay, so this is, again, I'm not going to get into too many details of this. I will just show you the examples. So this is some expansion of the black hole factor, the black hole solution. So this is a generalization of the black hole solution with the space-time dependent parameters. And then what you get at first order is this result. So for example, again, in the example where only this mu A source is non-zero, you get a non-trivial heat current that is sourced by vorticity. So this omega mu is vorticity. Okay, so there's again a non-trivial coefficient here. There is another term for the other heat currents. So there are two heat currents that are not the same because of this antisymmetry of the energy momentum tensor, which differs from this by this term. And there's an intrinsic torque, and there's a spin transport. So there's a corresponding of current, so spin current, that has two terms in it. One of them is sourced completely by the vorticity, and the other one is by the source mu A. Okay, so this is exactly like chiral vortical separation effect. So this JA is exactly the chiral current. Okay, so this is one of the components that I mentioned before. This corresponds to the chiral component, and it is sourced by vorticity. Okay, so with a coefficient that is given by this number. And then there's another term which is sourced by just the source mu A itself. And this term here, the first term, has already been studied. Something like this has been studied on the lattice, and this is called coined by Yamamoto and Imaki, the chiral torsional effect. So this is exactly the torsion, and as a result of the torsion, what you get is some chiral current. Okay, so this is that chiral torsional effect. And then so it's a bit different in our case because we also have this intrinsic torsion that they didn't study. So, but it's also very similar to what has been suggested by Barnett long time ago, this magnetization of an uncharged body by rotation, because essentially, so I'm talking about this vorticity term now. This is exactly what we see here. So we have, so we also see some, magnetization by rotation, and then you obtain some spin flow with a precise coefficient which you can calculate. Another side comment that I want to make here is that this Barnett effect, of course, is very old, and but very recently, it has been studied also in the nuclear, the analog of this Barnett effect by these gentlemen, and they see that this nice match between the theory calculation and the experiment. This is not our theory calculation; it's a different calculation. Okay, so I just want to mention that there are experiments going on also in that direction. So finally, there is a new kind of possibility for the spin transport that is not proportional to vorticity or these sources, but something else. And so this is a different example where I turn on another component of the source and set all the rest to 0. And then you get 3 different types of currents. One of them is proportional to this divergence term of the fluid. So it looks like exactly this kind of term would appear, for example, in sound waves. So this looks like there's some kind of a spin current generated by sound waves. And then you have, for example, this kind of effect, which is, so there's a vorticity term, and there is this term that is perpendicular to the source V2. So I would call it something like a vertical Hall spin current. So there's the bottom line of all of these examples is not that I want to make a direct connection with experiments yet, but I just want to make the observation that this is quite rich. So there's all kind of spin transport phenomena that you can generate if you turn on all possible sources. So there is still much to explore, I think. So this brings me to the end of my talk. So I just wanted to observe, first of all, that the torsion is quite important in all of this story. So this is the lowest order source for the spin current. And as I said in the beginning, you can set torsion to 0 at the end of the calculations, but it is quite important to establish the response. So you turn on torsion, you calculate the response, and then you can set it to 0 in the end. And then we derived hydrodynamic equations in the presence of torsion and constructed the constitutive relations. And then we used a kind of unorthodox theory, Lovelock-Chern-Simons gravity, because that is an example where you have an example of first order gravity where you have spin connection and field bind independent of each other to calculate the spin transport coefficient. So this gives some calculation. Okay, so this is just an example, some toy model that gives some results. Whether these results are universal, whether you can reproduce them by using more standard holographic techniques, that I don't know yet. So, so this all of this, I'm just going to flash it here and leave it for you to read. So thank you very much for your attention.
Yeah, thank you very much, Umut. This was indeed very interesting. And we already have some questions, and Masoud is the first.
Hi, thanks for the nice talk. I have two questions. And the first one is that can, for example, we use a K-radius 5, which
what?
A K-radius 5 solution. I'm talking about this example because from its boundary, people have found the solution to hydrodynamics and also to magnetohydrodynamics.
Right, exactly, yeah. So I think the most general thing that you can consider indeed is to, so in the usual approach to Einstein in holography, what we do is we use Einstein's theory coupled to some gauge fields, right? So you can indeed find some asymptotically ADS Kerr solution that corresponds to rotating plasma. And you can also turn on some magnetic charges there. So that will correspond to some finite magnetic field on the boundary. That is possible, but that wouldn't give you, it wouldn't make it easy to identify the spin transport, because spin transport is really directly sourced by the spin connection. So in that theory, the spin connection will be something derived. It will not be a source. It will be a derived quantity.
Yeah, I mean, there's no torsion in the metric, yeah? There's no torsion in the solution. Can you somehow engineer that solution and add torsion to that?
Well, not in that theory, I think. So you see, it may be possible. So in supergravity, we know that there is torsion. So in many examples in supergravity solutions, there are torsion, but they are really coming from the fermionic bulk fields. So if you have some bulk fields that are fermions, then it may be possible to engineer by turning on torsion that comes from them. But that would complicate the problem a lot, because then you have to solve also fermions in the bulk. Yeah, so right, I think it is possible. This is quite an interesting question, and this is what I want to also do. And this is one of the outlooks here, I think, right? So the derivation in a more general holographic theory is like using supergravity. So I think it's an open problem, but it's yeah.
And another question is a quick question. Are you using in the boosted black hole? Are you using a rigid rotation for the mu before giving it space-time dependency? Yeah.
Before, yes.
Yeah. Okay. Thank you.
Right. Okay.
Okay. The next one is Enrico. Is this true?
Hi. Yeah.
Hi.
Thank you. I actually found it very interesting. I have some maybe naive question, but so I'm not an expert of holography, so maybe, but anyways. So your theory is a conformal theory, right?
That's right.
So because you have to make the correspondence with the conformal theory, but that means that the mass of somehow the constituents of the fluid are 0, right? So
That's right.
in this case, why would I expect a transport which is very different from the usual chiral transport, in the sense that since for massless particles, the spin and momenta are somehow correlated, why would you think that introducing a spin tensor is actually a real extra degrees of freedom, or you know what I mean?
Yeah, sure. Because of the torsion in this theory. So essentially, so it is all coming from. So let me go back to this decomposition. It's gonna take some time. So indeed, so I was trying to make this comment during the talk, but so this mu A term here, for example, that is the axial. So that will be the axial chemical potential. So axial chemical potential is there. It's included in this decomposition. But
yeah,
there are other ones. There are other ones as well, because like all these other terms that that you usually don't really take into account, because here, so if you make a decomposition of the spin current in this form, so some of them, this is quite rich. So this transverse part. So this part you typically don't consider. But even in a conformal plasma, this is non-trivial. But indeed, it is related. So all these examples that I was discussing, so there are different solutions that you can get. But in this particular, so this last solution, for example, this let me show this one. So this one, for example, here is this is exactly like a chiral transport.
Yeah, right.
Right.
But I mean, after all, the spin of a massless particle, you do not define it as the spin of the massive particle. So you need to go to the rest frame. So in this sense, I would expect that, I don't know, I don't see how you can define a real spin. I mean, I would define a helicity transport rather than a spin transport. But okay. I mean, yeah, I don't.
No, but I mean, I think you break, if you want, you break conformality by introducing sources in the game. So
okay, you break.
Exactly. So if you want to send the sources to 0, then it's problematic. Here, for example, you see that this mu A is appearing in the bottom, right? So some of the terms, because so if you set mu A to 0, then you get a completely different set of solutions. And if so here I'm assuming that mu A is non-zero. If mu A is non-zero, then you get this kind of transport. So this is kind of disconnected from the limit mu A equals 0. So indeed you break conformality in this way.
Okay, I see.
Yeah.
Thanks.
Okay, Giorgio, please.
Yeah, a very basic question is that for holography to make sense, I mean, people can deviate from conformal symmetry, but to have a classical gravity, you need to have a planar limit. And you need to have a planar limit in the field theory end. And in every physical situation I can think of, sort of spin-orbit interactions are suppressed by NC. Or either fermion boson, fermion boson spin alignment is suppressed by NC, and boson-boson spin alignment is gauge dependent, I should say. In this picture, is there I mean, this is semi-classical, of course. Is there a way to think about this?
Yeah, very good question. So I think, so NC dependence is, so typically, let me go back to the action. So again, this is a different theory. This is different than the usual Einstein's theory, but in usual Einstein's theory, for example, here, there would be some Planck length, and that Planck length would be controlling the NC dependence. So you would take, for example, there would be something like an NC square here. So you would take it very large. And that of course, this parameter kappa enters in all of these calculations. So if you're lucky enough, then it would only appear like an NC square term. So that's just multiplying the spin transport coefficient with this number of degrees of freedom. So here, I don't know. I don't know how important the effects are, but yeah.
One has to be careful, because I mean, you have the non-spin effect for this theory to account for non-spin effects. And for spin effects which are NC suppressed, you have to go beyond the semi-classical limit, right?
Well,
You
here,
have fluctuations. Spin effects, in a big number of physical situations, effects of spin alignment are sort of quantum fluctuations. You see what I mean?
right? Yeah.
Yeah, and in this case, just if you look at SUNC, like the large N limit of QCD, spin alignment is NC suppressed. I mean, quark spin alignment with respect to gluons.
Well, yeah,
And
quark
gluons
spin
have
alignment.
H-dependent.
Yeah. So but it may. I mean, you see. So the thing is that well, the same question you can also ask for the different kind of transport. Whether they want to, well, there are different answers. So we use holography, for example, to study also energy flow and everything, but assuming that large N, finite N effects can be are small. So this is indeed, it's not going to give you a precise number, but it will just rather tell you certain effects that you may miss in the V coupling calculations. So like for example, what Yuri Ivanov mentioned in his talk, this chiral vortical effect. So the same kind of thing is true here, I think. So this number here, whether I would trust it or not, whether this kappa is going to like NC square with no coefficient in front, I don't know, because this is a toy model for me. But yeah, so that should be studied in more detail. But well, one last thing that I would like to say about this NC dependence is that indeed in this approximation by using hydrodynamics, I am not really focusing on how the spin transport is coherently produced by it's a collective effect of these individual particles, but rather just define it as a canonical degree of freedom in the theory. Right? So that is the collective degree of freedom in the theory, not canonical, collective degree of freedom in the theory by itself. So I don't know whether, from what kind of fermionic interactions this is produced.
Okay, Matthias has the next question.
Hi, Umut. Thanks for the talk.
Yes.
I have a very general question and then maybe a more technical one. The very general question is, you basically said something like this was the minimal setup that you could find under your criteria of finding analytic solutions and also including torsion in the background, right?
Yes.
My question is do you see another minimal model that might be satisfying this criterion? And maybe this question goes back to the question, is there Einstein gravity, and then you can add torsion on a level of a fluctuation maybe?
Yeah, that may be possible. I haven't thought about it in detail. That's a good idea to include it as a fluctuation. But I think what one can do as a more minimal setting is to consider lower dimensions. I mean, there's also already interesting for most of the condensed matter applications, for example. If you just consider 1+1 dimensional theory, like quantum wires, and so there, of course, there is no rotation, but there's still you can define torsion, including the the time component. And then the question would be, then you would be solving a 2+1 dimensional gravitational theory, and for that we know that there's a lot we can do. So that is one direction that I want to explore, but yeah. But in 5 dimensions, I think it's not obvious to me what else one can do.
Mm-hmm.
The technical question was?
Yeah, thank you. The technical question was, well, slightly more technical. I think it was on your slide 29, the spin current, like the response to the mu A. Yeah. So maybe I'm reading this wrong, but isn't this the temperature contribution to the, like, doesn't this look like the temperature contribution to the chiral vortical effect with the T squared times omega mu times the anomaly coefficient?
Right, this is what I said. It's chiral imbalance by chiral vortical separation, because this is axial, this is not...
Right, so basically 2 questions there. So is the chemical potential term lacking for some reason? I don't see it. It's probably me.
It's not turned on. There's no charge.
That's the mu v. Would that be?
Yeah, mu v is, there is no mu v
Okay.
in this theory. That's why. So I'm only turning on. I'm only turning on this source mu a.
Okay, and then on the holographic side, this t squared term is only there when higher curvature terms are taken into account, right?
I guess so, because in this theory there is an r squared.
Okay, so for seeing it, this particular response there, it was essential that that Gauss-Bonnet term was there.
I think so, yes, I think so. I think so. I didn't really, yeah, okay. So it's a good question. So it's, I have to double check what happens if you set this to 0. I don't think that we can find analytic solutions anyway, but it should be very essential for that, yes.
Okay, thank you.
Yeah.
And Xu Guang, you also have a question?
Yes. I'm not expert on holography, but as far as I understand, if you want to make the holography calculation, you need to solve out how your bulk field, in this case, you have the Fairbairn and also the spin connection,
yes,
behave near the boundary, right?
Yes.
And in this case, how do you set up the boundary condition for the Fairbairn and for the spin connection? And in this case, for example, if you before calculate the spin transport, if you calculate eta over s or some other usual transport coefficient, have you checked that you get the similar result?
So yeah, very good question. So here, well, first of all, the answer is this. So you have this bulk field. So let's discuss the spin connection. So you find a solution by solving the Einstein's equations with this asymptotically ADS space in that theory. You find a solution for the spin connection, and the spin connection, as r going to 0 towards the boundary, it decays with the particular coefficient that is completely fixed by the dimension of the operator. So there is a leading term and there is a non-leading term, sub-leading term, and the leading term is going to be exactly this, with some r to some power that is given by the dimension of this operator, and there is going to be a sub-leading term that whose coefficient is this. So here in this calculation itself, I didn't have to go through that calculation because we have a more direct way of obtaining the spin flow by essentially directly by reading it off from the expectation values. But yeah, so this is the answer. So there are two terms. One of them is determining the expectation value of the dual operator, and the other one is just the leading term, is just this source. So this source, this omega 0, for example, is one of these. So for example, in this example, that is this mu a, if you want. So this one. And the other question you had is indeed, yeah, so that's so if I just use this theory to calculate eta over s, whether I get 1 over 4 pi, the answer is no, you don't get 1 over 4 pi, you get 1 over 4 pi with some correction that is proportional to this Gauss-Bonnet coupling. So it's also well known that so you typically get 1 over 4 pi if you ignore these higher derivative corrections. In the presence of these higher derivative corrections, there is some correction to 1 over 4 pi. But that result is also known. So it's like 1 over 4 pi minus some number.
Okay. I see Masaru has a question.
Okay, thank you.
Yeah. So I have a very naive question. So in the first part of your talk, you show that some table of the independent number of the source, and but if you consider some specific theory like the QCD, and if you take the variation with respect to the spin connection, we know that the spin current is totally anti-symmetric, and it is a dual to the U1 axial current. So I don't know, here I think that you do not assume the specific tensor structure for the spin current, but
Yeah.
But
So here,
once you specify, yeah.
right. So here
It
I'm considering a more general, if you like, a decomposition. So here, what you are referring to is would be either of these two terms, I think. So you have so this says, so it is antisymmetric in these two indices A and B, but there's a mu index downstairs that is essentially telling you that is the space-time direction. So this is like the flow of spin whose orientation is given, it's perpendicular to this plane that is determined by these numbers A and B. And then there is this direction of that spin flow that is determined by this mu index here. So there are 24 degrees of freedom. So this is 6, there is another 4. So I'm including time as well in all of this discussion. So then I'm just doing the most general Lorentz covariant decomposition. So that includes the what you just mentioned, but it also includes these transverse terms. So here, for example, yeah. So here, I mean, let me give you an example. So for example, if you just take this and insert it in the covariant derivative of a spinor, of a fermion, from this term, you will get precisely what you're referring to. So because that would give, so that this gamma AB is contracted with the commutator of, sorry, this omega AB is contracted with the commutator of gamma A, gamma B. And then there's going to be a gamma beta term as well that contracts this in the Dirac equation. So that will be like gamma 5, and that will just give you gamma 5 when you contract all of that with these indices. So this will be precisely the axial charge. But then there are other terms as well. So that's which you should take into account in the presence of torsion.
See, but how should I consider it? Because so if you specify, for example, the microscopic theory is composed of the Dirac fermion, and if you take the variation with respect to spin connections, you will obtain just a totally antisymmetric spin current.
I mean, here this is going to be the totally antisymmetric part, but then there are other parts. Yeah.
Other part, this is just for the background field, so it okay. Maybe
it's the same thing. It's the same. So this is the background field, but this is exactly the thing that you plug in this in the covariant derivative of the fermion. So in here, that's it is. So I guess the confusion is coming because of torsion. So in the presence of torsion, you have new terms.
Okay. Okay, thank you.
Yeah. So then, one more question. Okay. I think we already over the roundtable discussion time. So anyway, Stefu, go ahead. Hello.
Hi.
Hello. Thank you very much for this nice talk. I have a naive question. Why the shear tensor is 0 in your models? So
it's because it's a because it's a toy model, indeed. So this
is so it's just because in your toy models. So in this model, do you still have the conventional linear term of curvature?
No, yeah. So sorry, you mean like this part, this tensor? Are you talking about this one?
No, at the end you have a expression. This is 0. Yeah. Somewhere.
There are different solutions that, for example, here this is not 0.
Right.
But I guess you are referring to this solution here. You have 0. So these are different solutions. Yes.
But do you still have this conventional linear term of curvature? Like,
yeah. So these are 0th order terms. So this is yeah. So thanks for asking this question. So here, so all of these examples that I mentioned, that I showed you, is they are showing the 0th order contributions to this shear tensor. So they are completely sourced by these contortion sources. So here, for example, you see that there is this is all proportional to the contortion sources. Mu A, this V2, C, and V2, they're all contortion. So if you set them to 0, you would get 0 indeed. So, but if you go to the higher order in the derivative expansion, you get what you expect to get, like the shear viscosity. Okay, so the viscosity terms are not, so they're higher order in derivative.
Okay.
Okay.
I would really like to, Giorgio, I'm gonna cut you now, and you can ask your question in the round table.
Sure.
Okay, good. So let's.
Because my question is more general, is for this,
Yeah.
but it's general.
Yeah, we have to make a plan. Okay, let's first thank Umut again. It was a very nice,
Thank you very much.
talk.